In this lecture, we will continue with a study of the properties of the Fourier transform. We have been talking about this property of translation in time. You recall that what we said here is, if f of t has a Fourier transform f j omega, then the same function shifted in time, translated in time by an amount d, f t minus d will have a Fourier transform which is f j omega multiplied by e to the power of minus j omega d. And we observed that the magnitude spectrum of f of t minus d and f of t remain one and the same, means only the phase spectrum gets shifted. The phase in fact gets smaller by an amount omega d proportional to omega. Let us work out an example how this property can be used to find out the Fourier transforms of certain signals. Suppose we take a function which follows the rule e to the power of minus a t for a finite duration from minus d to plus d and is 0 everywhere else. So, that is the function that we are talking about. We can find the Fourier transform by integrating this f of t multiplied by e to the power of minus j omega t from minus d to d. Alternately, we can make use of the properties of the linearity of the Fourier transform as well as the time shift property which we have just been discussing. What we can do is, this f of t can be thought of as composed of two functions like this plus another function starting here and decaying like this. The magnitude of this is of course e to the power of minus a t, therefore, this will be e to the power of a d. So, that is the amplitude of this, and this decays by exponentially as e to the power of minus a t from this point onwards. So, what we are saying is this composite function can be thought of as this continuous function like this would continues forever, and then you clip this tail by introducing a negative exponentially decaying function like this, which is given by this. Now, so what is the amplitude of this? This must be exactly equal to this, so that from that point onwards it decays to 0. So, this will be e to the minus of e to the power of minus a d. This quantity is e to the power of minus a d. So, a negative going form like this will do the trick. So, we have to find out the Fourier transform of this and the Fourier transform of this and add them up, that will give the Fourier transform of the composite wave. Now, to find the Fourier transform of this, what we can do is, let us shift this to by an amount d, so that this is e to the power of a d and this delays e to the power of a d multiplied by e to the power of minus a t, and this is an exponentially decaying function like this. If we know the Fourier transform of this, we can find the Fourier transform of this because this is translated in time by an amount d. Similarly, as far as this is concerned, if we can find the Fourier transform of this with an initial amplitude e to the power of minus a d, then you can find the Fourier transform of this. And this is a function for which we already have, you recall that we said e to the power of minus a t u t has the Fourier transform of 1 over j omega plus a. This is something which we already found out. So, as far as this is concerned, its Fourier transform would be, instead of unit amplitude e to the power of minus 1 at time t equals 0, it has an amplitude e to the power of ad. So, this the Fourier transform of this would be e to the power of ad. The Fourier transform of this would be e to the power of ad divided by j omega plus a. 1 over j omega plus a would be the Fourier transform of an exponentially decaying function starting with the unit amplitude to start with, but since this has an amplitude e to the power of ad to start with, it is e to the power of ad by j omega plus a. Now, coming from here, how do we go to this? If this is f of t, this is f of t plus d, because it is advanced in time. If you call this f of t, this will be f of t plus d. So, we go back to this rule. This rule applies incidentally whether d is positive or negative. So, if this is f of j omega for this, as far as this waveform is concerned, it is e to the power of ad by j omega plus a multiplied by e to the power of j omega d. J omega d. Now, coming to this, this is similar to this, except that it has an initial value of minus e to the power of minus ad. Therefore, the Fourier transform of this would be e to the power of minus ad by j omega plus a with a minus sign, because it is the amplitude to start with is negative. Now, this function is nothing but this, except it is delayed by d units. This is minus d here and this is plus d. Therefore, the Fourier transform for this is minus of e to the power of minus ad divided by j omega plus a multiplied by e to the power of minus j omega. So, we found out the Fourier transforms of these two. So, the Fourier transform of this would be just the sum of this, because Fourier transform follows the linearity property. That is, if f1 of t and f2 of t have Fourier transforms f1 j omega and f2 j omega, the Fourier transform of c1 f1 of t and c2 f2 of t would be c1 f1 of j omega plus c2 f2 of j omega, irrespective of the values of c1 and c2 constants. So, the Fourier transform of this is now given by the sum of these two, which of course has a common factor j omega plus a I can keep outside, and you have e to the power of a plus j omega d minus e to the power of minus a plus j omega d. So, this example shows us that if we recognize a function as composed of a linear combination of functions whose Fourier transforms we already know, we can intelligently get the Fourier transform of this without having to do the integration starting from scratch. Okay. Let us take up the next property. Just like you have translation in time, we can think of translation in frequency axis. Which is equivalent to multiplication by e to the power of j omega c t. Note what we have here. In the property 2, we have a translation in time axis. F of t goes to f of t minus d. In the transform domain, f of j omega gets multiplied by an exponential quantity. In a similar fashion, what we have here is, if we multiply in the time by e to the power of j omega c t, the Fourier transform gets shifted in the frequency axis. What happens is this: if f of t has the Fourier transform f j omega, then what we would like to know is what is the Fourier transform of f of t multiplied by e to the power of j omega c t. This is the question which we would like to ask. I multiply f of t by an exponential function e to the power of j omega c t and would like to know what its Fourier transform is going to be. So, let us do this. The Fourier transform of f of t e to the power of j omega c t by definition is minus infinity to plus infinity of f of t e to the power of j omega c t multiplied by e to the power of minus j omega t dt. And this is straight away seen to be minus infinity to plus infinity of f of t e to the power of minus of j omega minus omega c t. Now, if we had f of t e to the power of minus j omega t dt, this would have called it f of j omega. All we have now is instead of omega, we have got omega minus omega c. So, it is almost the same as the defining relationship of the Fourier transform of f of t, except that instead of omega, you have got omega minus omega c. So, this obviously will be f of j, instead of omega, you have got omega minus omega c. Which means that the Fourier transform of this is f of j omega. This is the same Fourier transform, except that the spectrum gets displaced by an amount omega c. So, whatever value it takes at a particular value of omega, it takes the same when omega minus omega c takes that particular value, the function will have the same values. So, this is again an important relation which will be useful in the context of modulation of signals, amplitude modulation of signals, where f of t is really multiplied by, instead of e to the power of j omega c, something like cosine omega c t or sin omega c t. We will take this up, we will show that presently. But you notice the duality between the property of translation in time and the translation in frequency. When you are translating the function of time, then in the transform domain, the transform gets multiplied by an exponential term. If you are translating it in the frequency domain, as we have done here, then in the time domain it gets multiplied by e to the power of j omega c t. So, there is a duality between the transform domain and the time domain. Now, let us carry this as an illustration of this. Let us take up a case where f of t is multiplied not by e to the power of j omega c t, but cos omega c t. As an application of this property, let us take this example. Where f of t is multiplied by cosine of omega c t. We would like to find out its Fourier transform. Now, we can express this of course as 1/2 of f of t multiplied by e to the power of j omega c t plus e to the power of minus j omega c t, because cosine omega c t is expressed as e to the power of j omega c t plus e to the power of minus j omega c t divided by 2. So, obviously then we have two terms, half f t e to the power of j omega c t, half f t e to the power of minus j omega c t. We observed in this property that if we have f of t e to the power of minus j omega c t, then the Fourier transform is f of j omega minus omega c. If we had minus j omega c t, this would have been omega plus omega c. So, we used those two properties, that property, and then find the Fourier transform of this. So, the Fourier transform of this would be 1/2 of f of j omega plus omega c and f of j omega minus omega c. That is what we have got. So, what is the implication of this? Let us see. Suppose I have an f of t and the corresponding Fourier transform, Fourier spectrum. Let us say it is like this. Imagine it is like this. It is amplitude spectrum which is symmetrical. Something like this. Suppose we call this, just for the sake for reference, let us call this A. This is 0. These two form a Fourier transform pair. Now, when you are talking about f of t cos omega c t, the spectrum for this now consists of two sections. One is half of f of j omega plus omega c, another is half of f of j omega minus omega c. This portion is now centered around omega c, and then it will have the same spectrum is reproduced here, except that it is centered around omega c instead of the origin. Therefore, it will have something like this. If this is A, this would be A by 2, because it is half of that. Similarly, f of j omega plus omega c is a spectrum which is similar to this, except that it is reduced by a scale factor half and is advanced by an amount equal to omega c. Therefore, it will be centered around minus omega c. So, it will be like this. So, this is the spectrum of this quantity. And what is the how is the spectrum related to the original spectrum? We can say that the original spectrum gets split up into two halves, equal halves, and one half shifts forward and sits around omega c instead of 0. The other half is shifted in the reverse direction and centered around minus omega c instead of 0. That means the essential shape of the spectrum remains the same, except that instead of being centered around the origin in the frequency domain, it is centered around omega c and minus omega c. And this is a commonplace operation in communications in the amplitude modulation, where the information content of a signal is purposely shifted from the, instead of being centered around the DC, it is shifted to a more convenient location on the frequency axis. It is shifted to be centered around plus omega c or minus omega c. This is called the carrier frequency. This is done in the interest of two things. One, first of all, for the transmission of the information, it will be more convenient if the information is centered around a higher frequency rather than the DC. And secondly, the same channel, communication channel, can be more effectively used by having several items of information in a more convenient location. Instead of that is, you can have another information channel here, another information channel here, and therefore it makes for more effective communication for a given channel. Because of these reasons, it is convenient to modulate a signal f of t by multiplying by a trigonometric function of this type. These details of this, of course, you will learn in your communication theory, but as far as we are concerned, we just want to point out an application of this property of the Fourier transform. Now, let us take up the next property,